Happy exam week. We have an assignment Wednesday, a review session planned for Thursday, and then an exam Friday. Study guides posted. So if you haven't had a chance to take a look at that, I highly recommend it in the reasonably near future. Questions on schedule? Okay. We were just finishing up the context-free pumping lemma last time. So we were going to recap this example, get through the last little bit of this, and then it's on to bigger and better things, which is probably a bit of a relief. By the time we reach this point in the quarter, I'm as done with pumping lemmas as you all are. All right, so this example was the string followed by the exact same string, which was very similar to our WWR example, except that we noted that it would be much nicer if we had a queue to follow along with us rather than a stack. If we had a queue, we could recognize WW. Since we don't and we have a stack, there became a big issue when trying to recognize this language. So to show it's not context-free, we picked a good string, A to the M, B to the M, A to the M, B to the M, which is the same string, A to the M, B to the M, repeated again. We looked into what can, thinking of this from the pumping lemma game perspective, player one can pick anything. So we need to consider the associated cases of what they could pick. For the recursion aspect Vy, this could be in all A's, it could be in some A's followed by some B's, it could be in all B's, or it could be in some B's followed by A's. And once again, it doesn't really matter what I you pick here. On the slide, I pick I equals 0. I think in class we went over I equals 2. Doesn't really matter. Anything will work here. We're going to break these down into some templates that we could work with the cases with. So the first was all of one character. So if they were all A's or if they were all B's, then we could attach ourselves to, well, if it's all A's and no B's, then the A to the M, A to the M aspect of this is going to be broken. They need to be the same number of A's in the first W as there are in the second W. And if player one picks something that's all A's, one of those will be more than the other. Same with B's. If there are some A's and some B's, so starts with some A's, ends with some B's, then we're in either the first W or the second W. And regardless, we're going to be increasing the number of A's and B's in the first W or the second W and not the associated other. And if they pick some B's followed by some A's, then they're going to be increasing the B's in the first half relative to the B's in the second half, and they're going to be increasing the A's in the second half relative to the A's in the first half. So there's always something that you can attach yourself to that makes a good intuitive argument. Of course, we're kind of on the line here between an intuitive argument and a math proof, so we need to take this a little bit deeper just to be able to show for sure this is the case. So here are some intuitive arguments for each of those. Seeing it a bit visually is also nice. So we have our A to the M, B to the M, A to the M, B to the M. Player one is breaking this down into U, V, X, Y, Z in some capacity. We just have to be able to prove that for any potential breakdown of where V, X, Y is in the string, that we can pump it some number of times to get a string that is not in the associated language WW. How are we doing? Example 2 makes sense? Anything to follow up on? Excuse me. We'll move on to the third example. How about A to the N factorial being not context-free? Any intuition for a string you want to pick?
A to the m factorial.
A to the m factorial? I like it. Why is that a good choice?
I don't know, I'm not sure yet, but given the other problems, and given that I think we're going to be proving that there would be maybe something that is not a multiple of m factorial or something like that.
Yeah, yeah, we knew we needed m in there somewhere, and it has to be in the language. So m factorial is really the only thing we can attach ourselves to. It's just the difference between a to the m factorial, m minus 1 factorial, m plus 1 factorial. A to the m factorial will work. Anyone have some intuition they want to share?
I don't know, just thinking about it, I think that if we repeat in the VXY sequence, we're either repeating one A or two A's. both sides. So naturally, I feel like if you're adding an a to more than a to the m factorial, you're not in that language of m factorial, because you're adding an extra 8 or an extra 2 a's.
Yeah, we need to get to the next factorial with something like I equals 2.
Yes, but you can't do that.
We have to be able to show that mathematically,
Okay.
which is an excellent point to hold on to, because that is a very good intuitive conclusion. What's the cap? What are the most a's we're adding to this? What is the largest that by could be?
M.
So we're adding at most m a's, and we need to reach m plus 1 factorial.
It's impossible.
Yeah, that certainly seems like it's going to be a stretch. We need to multiply the current number of a's that we have by m plus 1. If we broke that down into multiplying it by m, and then adding in the plus 1, what does the plus 1 do for us? Instantiate the problem, maybe that would help. If we have 5 factorial being 120, to get to m plus 1 factorial, we need to multiply the number of m's by 6. You could break that down into multiplying it by 5 and then adding another m, or another 5 factorial, break it down into 5 copies and 1 copy, and the 1 copy is already larger than, you can already show the larger than the possibility. So there are a couple ways to do this. One of the ways that's on the slide is pulled right out of the book. For me, intuitively, I want to break this down into its components. If we're taking m, which is 5, and looking at 5 factorial being 120 a's, and to get to the next factorial, we have to multiply that by 6. We could think of it doing it that way, breaking down the m plus 1 factorial into the 5 factorial, and then there's it's 6 times 5 factorial, so here's 5 copies and here's 1 copy of the 5 factorial. So if we're adding m to this, can we break this down into some way that we can compare these and show that one is greater than the other? That's my intuitive hint for how I would handle this without the book. Let's go through the book's logic as well. We're going to instantiate a couple of other variables called k and l that are the number of b's and y's, the number that are associated with the left-hand side of the recursion and right-hand side of the recursion. If we want to look at the string u with xz, the part that is guaranteed, the part that's without the recursion, we just take the m factorial and subtract out the number of the left-hand side of the recursion and the right-hand side of the recursion. This pump now must produce the next factorial. So we have to be able to go from, this is subtracting k plus l, we need to get to m minus 1 factorial by subtracting out k and l. So we're going to say, kind of proof by contradiction again, that sure, that's possible. M factorial minus k plus j equals j factorial for some j. So k plus l must be less than m because of the pumping limit constraint. So we can grow this out and show that m factorial minus k plus l has to be greater than m minus 1 factorial. And we know this to be true. Therefore, no possible j exists that will satisfy the above. But again, we need one more step really to show that this is true. M minus 1 factorial, that's a difference of at least the value of between m minus 1 and m factorial. We're multiplying it by m, and since this can be at most m, we're subtracting off something that is less than m. So there's no way that could be greater. Not the most proof-based argument, but it works. So you can either attach yourself to I equals 0 or I equals 2, doesn't really matter. This logic will work regardless. Maybe one more mathematical example, since those tend to show up on things. A to the n, b to the j, such that n is equal to j squared. Again, let's think intuitively first. Why wouldn't this be context-free? First of all, are there more A's or more B's in most cases, as long as n isn't 1?
A's.
There are more A's. You have to square the B's to get to the A's. That makes sense. So thinking about this with a stack, how would you try to handle this? You read in some A's, and those A's have to be a perfect square. How are you handling that case where you're trying to check whether it's a perfect square while you're adding them to the stack? How do we get from a square to the next square? Anyone know that pattern? What is the sum pattern for squares? Anyone know that off the top of their head?
Isn't this stuff?
Probably. If you add the odds and you just add different segments of this together, you get 1, you get 4, you get 9, you get 16, you get 25. So you get the perfect squares as you add the odd numbers in sequence. So if we're looking for a perfect square, we have to somehow, while we're adding A's to the stack, be checking odd, add the next odd, add the next odd, add the next odd. Is there a way to do that?
No.
Not really. Even if there were a way to do that, we'd have to be able to take the square root of that value once we were done and check that against the b's. That seems like it's going to be unlikely to be successful with just a stack. All right, so now how might we be able to go through mathematically and show that this is not context-free? Here's the visual reasoning for perfect squares. We start with 1, then we add that as an extra row and column, and then add the extra completion of the square, which is always 1. Then the extra row and column complete the square, row, column, complete the square, row, column, complete the square. So the sum of each one of these, so we get 1, 3, 5, 7, 9. And each one of those, you're adding in the next layer. That becomes a complete square. You're just building the area of that complete square recursively. Another fun application of recursion. What do we pick as our string?
I said a to the n, b to the m, n is equal to m squared.
Okay,
So I just replaced j squared m.
okay.
Well, not, I replaced j with m.
Yeah, j with m, so that you ended up with a to the m squared, b to the m. See, well, it's the equivalent, basically. Yep, I like that as a choice. It fits the language, and I don't see how we need to do anything fancy here. We can't do it in its base form. There's no trick that's going to help us out here. So you can visualize it in terms of, all right, well, we have some cases. We know that either by is all a's, by is all b's, or either a is all b's, b is all y's. A's and b's have overlaps between b and y in some capacity. That's going to be a little bit scary. So yeah, bxy can be all a's, some a's and some b's, or all b's. And the some a's and some b's case is what ends up being a challenge here. If you attach yourself to the all a's case, that's relatively easy to show. The all b's case, that's relatively easy to show. There's a perfect balance right now between that square and its root, or m and its square. You add all a's, there's no way that by adding at least one a to m squared, that it's going to be a perfect square for m, since you're making no change to m. Make a change to m, what was the perfect square to m isn't going to be the perfect square to m plus 1 or m minus 1. The hard part is these some a's and some b's, because we don't know anything about the breakdown of bxy. Basically, is there a position where we could perfectly place a dividing line somewhere in bxy, where when we scale that b and the y, we're scaling the m and the square at the same rate, at the appropriate rate. You have to be able to show that no, that's not possible. Any thoughts on how we would do that? This is a mathematical challenge worthy of a homework problem. Let's take a look at the case of b is all a's, y is all b's. That means that there is a place somehow where we can put the perfect number of b's to scale by the square and the perfect number of y to scale the base. So we're scaling the base and we're scaling the square at the same time. So if we scale the base, we know we need to add the next odd number to get to the next square. So if one of these is empty, it defaults to one of the existing cases. That makes sense. If the length of v is empty, then vy is all v's. We already proved that. If y is empty, then v is all a's. We already proved that. So we know at this point that v and y contain at least one character, because if they don't, we can default to a case that we've already shown. So we know, again, at least one. We could now say something like, okay, what is the difference between, now we're going to square the left-hand side of this, m minus the length of y, because if we take that out, we take out the length of y characters from m, that's going to be the base of the new square. And we need to show that that has to be less than or equal to m minus 1 squared. Because if we take 1 away, that's the minimum number that we could take from y. So we need to show that we can't reach the next square down. How could we do that? Well, let's FOIL out the m minus 1 squared, giving us m squared minus 2m plus 1. We also know that what gets subtracted from that m squared is the length of v. So we can replace the 2m plus 1 with the length of v. So now we've subtracted the length of y from the left-hand side to get to the new base of the square. When we FOIL out that square, we see that it's m squared minus exactly how much we would have to take away to be able to get to that next square. That's what v represented. But when we FOIL out that 1, we see that in fact 2m plus 1 is larger than that 1, that component that we possibly could have. So because of that result, we're basically done at that point. We just have to show that that 2m plus 1 has to be greater than the base that we took out, which has to be the case. This again is not the most straightforward, but it's more of a mathematical kind of problem. Relies on an intuition, a math intuition, finding equivalences and making an argument based on that. Questions on the pumping limit in general? Questions on applications to problems? I'm sure we will have fun again when we find these on homeworks and have some questions, but that's also okay. Maybe what I could get at this point then is a show of thumbs of how intuitive do you feel using the pumping lemma? I'm going to say regardless of the math part, because that's a little bit different and I want to see them separately from each other, but using the pumping lemma with regards to applying it to these kinds of problems, how intuitive does that feel? Does it make sense? Looks like we definitely need some more practice. This is the practice that I have on our slides. I will probably consider getting some more examples ahead of the exam that this is on. This is not on the exam that is this Friday. But I'll see what I can do with getting some more examples ahead of that. All right. So it turns out that this isn't the only interesting pumping lemma in other language types. There are other pumping lemmas that are out there that work very similarly. Before I scare you too much, you're not going to need to do any of these. I'm just describing how the pumping lemmas are used for other language classes that we have seen. But linear languages are one that we have seen. There was a distinction between those and context-free grammars earlier, but we can make a further distinction. A language is linear if there exists a linear context-free grammar for it. And every linear language is context-free, but not every context-free language is linear. And this mapped to the same class of language as the deterministic push-down automata. So if you can derive a nonlinear grammar for a grammar, it doesn't imply that it's not linear. In order to prove a language isn't linear, we have to prove that we could not create any linear grammar for it, which means that we need another pumping lemma. But the form of the pumping lemma for linear languages is very similar to the form for context-free, with one interesting difference. We could say exactly the same decomposition as we have for context-free, except that we get this very interesting additional, instead of vxy, the length of vxy being less than or equal to m, we're going to say the length of uvyz is less than or equal to m. And this shows that we can get to the associated recursion and complete the recursion in fewer than m steps, which is actually very similar to the regular language pumping lemma, where we needed to get to the cycle and complete the cycle. This is getting to the version of a cycle that is a recursive cycle. It's the recursion version of that, and complete that. And again, the length of vy has to be greater than or equal to 1, but now we know that the cycle, this recursion, is occurring in the first m productions of the grammar. So that means that we're going to get there by the time we've exhausted the productions, which is a useful thing that we can do. So what's the difference? Pump substrings would have to be within m characters of the left and right ends of w, which is very interesting. So the first half of that recursion occurs within m characters. The end of that recursion occurs within m characters. So instead of a sliding window of any size of length m, it has to be docked to either the left-hand side or the right-hand side in some capacity. So middle string can be arbitrarily lengthed. It doesn't matter how long it takes us to get to the end of the recursion from there, but we have to see that recursion within the first m characters at the start and end of the string. So how to solve problems like this are very similar to the context-free pumping lemma logic. So we don't go into it in significantly more detail because it's exactly the same idea. No homework or exam questions on the topic, but just thought it was worth showing that these pumping lemmas can be extended for many of the classes of languages that we care about in computer science. Right. On to bigger and better things. I guess we have some final thoughts here. Another very short slide deck. Before we move on to Turing machines, which are very interesting and have a significant effect on how modern programming languages have come to be, we want to be able to see things like what can we do with context-free languages that might help us to be able to better understand them, since this is the parsing part of a compiler. It's very useful to see what we can do to this class of languages. So the first, what kinds of closure can we get? So I guess I should go back and say, do we remember what closure is? Or just who can summarize the concept of closure for us real quick? If I were to say something like integers are closed under addition, what does that mean?
that their value is resolved from a variable.
So if we have two integers and we add them together, there's something that we can guarantee about the result. That it's an integer. Yeah, so we have an operation and we have some inputs to that operation. And when we talk about a closure under a particular language class, we're saying given inputs that belong to that class and an operation, the result of that operation is another one of those kinds of objects. So a context-free language, what can we do with context-free languages? We have two context-free languages. Can we union them together and guarantee that we get a context-free language? Can we intersect them and guarantee that we get a context-free language? Can we take the set difference and guarantee that we get a context-free language? So are they closed under union? Might be a first good question to ask. We actually tackled this earlier. What was our conclusion with regards to context-free languages and their union? What's a way to think of that? We had a grammar for the left-hand side and a grammar for the right-hand side. We just needed to add a rule in order to make a context-free grammar for the union. We had so here are our two grammars that represent language 1 and language 2, both being context-free. These are our start non-terminals for each of these grammars. Then to define and to show that the union of these two sets is context-free, we just needed to add one more production that allowed us to non-deterministically choose the left-hand side or the right-hand side as the language that was going to accept it. If both accept it, then it doesn't matter what we pick. But with non-determinism, one of these is going to return success, the other is going to return success, or they're both going to return success, which is the definition of set union. So it makes sense that context-free languages are closed under union. How about concatenation? Any thoughts on how we might be able to see context-free languages as closed under concatenation? We take a context-free language and another context-free language, and now we're going to say any string that this accepts and string that that accepts, we're going to concatenate them together and accept that in the new concatenation language. How do we think of this in terms of grammars?
But if you have L1 and L2, concatenating them would be S goes to L1, L2.
Yeah, we have our start non-terminals for each of those. We're just going to add a new rule. It says S arrow SL1, SL2. Yeah, that's exactly all we have to do. So it makes sense. They're closed under concatenation. I'll draw that out just so that people can have the notes. So instead of an or, we just concatenate. When we concatenate, we have the structure that we need to break this apart into its components. And we would use the exact language, the grammar definitions for L1 and L2 that we had before. They're closed under star closure for a very similar reason. How would we now represent something like L1 star? We have an SL1 arrow, some stuff. How could we show that the star closure is context-free? This one's a little bit harder. But thoughts on this?
I think SL1, SL1, or lambda?
Yeah, so we need some ability at this point, whatever this is, we're going to add something like an SL1, SL1, which allows us to now recurse through this any number of times. We can now create a concatenation of two, have one of these become 2 and 3, have one of those become 3 and 4, etc. But we also need the ability, since it's the star closure, to do it 0 times. So we need to make sure that that lambda is there as well. Yes, exactly right. So whatever already exists, just add these two components, and we can allow for the star closure. Some interesting things that context-free languages are not closed under. First one is intersection. Any thoughts on why, any intuition for why context-free languages aren't closed under intersection? Why doesn't the result have to be a context-free language if we intersect them? That seems strange. We're going to take a subset of a context-free language. Why wouldn't the result be context-free? Necessarily. I like to think of it with regards to if we're taking the intersection of this, we're imagining that we have, it's easier for me to visualize this as an NPDA, where we have stacks keeping track of the languages on both sides. If we take the intersection, that means that the language has to, the string has to be there in both of the stacks. So we need to determine those at the same time. And then find a way to return not if one or the other returns true, but now we need both to return true. And there's no way to come up with multiple threads and say, can these threads come back together in unison? There's no way for us to do that. So even though it is a smaller language in terms of we're restricting it further, there's no guarantee that it's countable or has rules that are as easy to disseminate as each of the individual components are. Also not closed under complementation. So we take a context-free language, we take its complement, there's no guarantee that the end result of that is context-free. But there are some subsets of these rules that are interesting. If instead of a context-free language and a context-free language, when we take the intersection, if one of those languages is context-free and one of them is regular, the result of that is guaranteed to be context-free. This helps us to be able to do things like, that should be a to the n, b to the n, sorry. A to the n, b to the n, such that n is greater than or equal to 0, but not 100 is context-free. So one of those is context-free, greater than or equal to 0, and one of them is regular, not 100. So we take the intersection of that, and we know that the result is context-free. We just have to count out to 100 and reject exactly that result. But we can do that with a regular language. So yeah, what does that grammar look like? It's disgusting, because we have to have a production that goes all the way out to 99 and allows for 99 or fewer, and another one that allows for 101 or more. But it is possible. It's just bloated. So instead of writing a grammar that looks disgusting or drawing an NPDA that would look disgusting, we can use this rule to be able to show that the resulting language is context-free, and that is a big shortcut for us. That ends up working really nicely. So some fun side cases where it would be gross to use the pumping lemma in a way that is something like, all right, let's prove this is not context-free by pumping lemma. Here's an example. Over the alphabet, A's and B's and C's, we want to show that the number of A's is equal to the number of B's is equal to the number of C's. We want to show that that language is not context-free. And of course, we could absolutely go through the pumping lemma for that. But it turns out that there's a much simpler, easier way of proving that this language is not context-free. And that's by showing that if it were context-free, then there existed a regular language that we could take the intersection of and force the result to be context-free. So we'll start with our assumption it's context-free. If it is, we can take the intersection of this language and another language that we can show as regular, A star, B star, C star. That's a regular expression, right? So by definition, that's regular. So let's look at what happens if we take the intersection of the number of A's in W is equal to the number of B's in W is equal to the number of C's in W and this regular language. What is the intersection of those two languages? What strings belong to both of them?
Where A is the number of A's is equal to the number of B's was the number of C's. Isn't that the intersection?
So that was what we started with. So we're saying that everything that's in there is in there, which is true. But what is the set that's in both? ABC is in there. What else? The empty string would be in there. There are strings that are in both of these. But what is A star, B star, C star saying? It's a guarantee on the order. It's saying all the A's come before all the B's come before all the C's. So it's a way of restricting the language class from caring about just the number of characters being the same to now they must come up in that order, which gives us what language? A to the N, B to the N, C to the N? Have we seen something about this language before? Did we already solved this with the context-free pumping lemma? We showed that this cannot be context-free. So since we've already shown that this is not context-free, rather than showing the number of A's equal to the number of B's equal to the number of C's is not context-free, use the concept of if we take the intersection of a context-free language and a regular language, the result needs to be context-free. So if L were context-free, then the resulting intersection would also be context-free. Since we know this is not context-free, the only assumption that we made was that L was context-free. So it cannot be context-free. Let's see if I can quickly go through this. So we start with something fresh. This is the last slide here. We've seen before that no algorithm exists for determining whether two context-free grammars generate the same language. It's very easy to prove they don't. We just have to find a counterexample. So that's another fun limitation to that logic. There's no way to determine whether two context-free grammars generate the same language. At least the ability to do that in general. But imagine if that counterexample doesn't exist. We're going to get into Turing machines here in a second in ways that says, so you've crunched this for 1,000 years and you haven't found a counterexample. Does that mean the counterexample doesn't exist? Not necessarily, we just haven't found it yet. It's ambiguous between a language where the counterexample exists, it's just deep enough in the grammar that we haven't found it yet, and a counterexample not existing. So there's no way for us to be able to terminate that at any point and say, well, the ambiguity has been removed. They don't necessarily generate the same language, or they do generate the same language. We have to find that counterexample. But if we haven't found it yet, who knows if we ever will. We'll come back and start talking about Turing machines and really start diving into the theory of computation part of the class. starting tomorrow. This is my favorite part of the class. It's exciting. We moved from pumping levels, which are not my favorite part of the class, to this, which is my favorite part of the class.
These are like.
Yeah, I think so.
It has, you hesitated there.
I wouldn't call it easy, but I'd call it a little easier to see the value of, I guess.